Welcome to this explainer. Today, we're doing something a little different. We're shifting gears. We're taking those Python coding skills you've already built up, and we're stepping right into the shoes of a software architect. We're going to look at how to design robust, scalable, and truly professional software systems using structural design patterns. So if you've ever wondered how massive applications are built without just, collapsing under their own weight, you are absolutely in the right place. Let's dive in.
Think about the modern apps you use every single day. How do massive, complex systems like Google Drive, Zoom, and Microsoft Teams actually work together without completely breaking down? I mean, when you click a button in your learning management system and it seamlessly opens a Zoom meeting or grabs a file from a cloud drive, what is actually happening behind the scenes? There's this huge, invisible web of integrations powering our digital lives. And honestly, making that happen reliably is one of the hardest jobs in software engineering.
Because let's be real for a second, the reality of integration is usually incredibly messy. When you're building a modern app, you aren't building it in a bubble. You're forcing your code to talk to payment gateways, remote databases, cloud services, external APIs, and a whole bunch of third-party libraries. If you try to just force all these different technologies to communicate without a structured approach, you end up with what developers lovingly call spaghetti code. The systems become tightly coupled and just incredibly fragile. If one payment gateway updates its API, your entire application might crash. It is a total nightmare to maintain.
Okay, let's anchor this to what we already know. You might remember our previous discussions on creational patterns, like a crane lifting blocks, focusing on how objects are safely and efficiently created. And while behavioral patterns cover how those objects communicate, today we are pivoting to structural patterns. We're focusing on how the puzzle pieces actually lock together. We're moving past the creation phase to focus entirely on connection.
So what exactly are they? By definition, structural design patterns are the blueprints that describe how classes and objects are combined to create larger, flexible, and maintainable software systems. Think of them like specialized building blocks. On their own, an object is just a brick, but structural patterns give you the mortar and the architectural blueprints to connect those bricks seamlessly, forming a stable, scalable application that can stand the test of time.
So why do these structural patterns matter so much in the real world? Well, they offer immense benefits. Improved flexibility, way better code reuse, and drastically reduced coupling. Let's bring this to life with a higher national computing scenario. Imagine you're building a student information system for a college. That system needs to talk to the library system for book checkouts and the attendance system for tracking. If you use structural patterns, you can connect these systems without rewriting your core code for every single new integration. Your code basically becomes a plug-and-play architecture.
To achieve this architectural nirvana, we turn to the legendary Gang of Four toolkit. The Gang of Four identified exactly 7 specific structural patterns to solve these massive integration headaches. Think of this as your professional utility belt for software architecture.
Let's look at the entire toolkit at a glance. We have the adapter, which converts incompatible interfaces, the bridge to separate an abstraction from its implementation, the composite pattern allowing you to group objects and treat them as a single entity. We've got the decorator for adding behavior dynamically, and the facade for simplifying highly complex subsystems. Finally, we have the flyweight to save massive amounts of memory when dealing with thousands of objects, and the proxy, which acts kind of like a bouncer to control access to objects. Every single pattern here has a highly specific job it was hired to do.
The key takeaway here is that selecting a pattern is never, ever about personal preference. It's all about precision. It's about matching your specific architectural problem to the correct structural solution. Struggling with legacy API integration? You reach for the adapter. Need feature extension on the fly? Grab the decorator. Simplifying a ton of classes? You need a facade. As an architect, your job is to diagnose the problem correctly so you can apply the exact right pattern from this guide.
Let's move from the bird's eye view to a deep dive. For the next few minutes, we're going to focus on the ultimate hero of system integration, the adapter pattern.
By definition, the adapter pattern allows classes with completely incompatible interfaces to work together by acting as a translator between them. I really want you to focus heavily on that word, translator. The adapter sits right in the middle of two systems that absolutely refuse to communicate in the same language, and it translates the requests so everything flows smoothly.
To really make this click, let's use a brilliant real-life analogy. Imagine you're traveling from India to the UK. You've got an Indian charger for your laptop, but your hotel room only has UK electrical sockets. The charger and the socket are completely incompatible. You can't just force them together without breaking something, right? So what do? You buy a travel adapter. The adapter doesn't change how the charger works, and it definitely doesn't rewire the hotel's electricity. It just sits in the middle and translates the connection. In software, the adapter pattern does the exact same thing for your code.
Let's apply this directly to our higher national computing scenario. Imagine your college has a payment portal that was built, say, 10 years ago, using a legacy payment API. It expects data in a very specific, old format. Now the college partners with a brand new bank that provides a modern payment API, which uses modern JSON formatting. They are totally incompatible. Instead of spending weeks rewriting the entire college portal to understand the new bank, you simply write an adapter class. The portal talks to the adapter in the old language, and the adapter translates it to the new bank in real time. It's incredibly efficient and safe. And actually, later in this session, you're going to take this exact scenario and implement this adapter yourself in Python.
While the adapter is all about fixing incompatibilities, let's look ahead to two other crucial tools in the toolkit, the Decorator and the Facade. Sometimes your systems can talk to each other just fine, but they're just too complicated to manage, or maybe they need new features without breaking existing code. That is exactly where these two patterns shine.
The Decorator pattern is an absolute lifesaver when your problem is feature extension. It's a structural pattern used to add behavior to an object dynamically without altering its core structure. Imagine you have a basic user object in your code. Suddenly, you need to add email notification capabilities, and then, a week later, SMS capabilities. Instead of creating a massive, complicated subclass for every possible combination, you just decorate the base object with new behaviors exactly when you need them. This keeps your base code clean and untouched. This is another pattern you'll be implementing directly in Python today.
And then we have the facade pattern. This is designed to simplify complex subsystems by providing a unified, higher-level interface. A classic example is a home theater system. To watch a movie, you have to turn on the TV, switch the input, turn on the soundbar, dim the smart lights, and start the media player. That is a lot of complex steps. A facade is like a smart remote with a single Watch Movie button. You click the one button on the facade, and it handles all the messy, complex subsystem commands behind the scenes. Your code interacts with the simple facade, not the tangled web underneath.
As we wrap up our look at the toolkit today, it's important to acknowledge the remaining patterns: the bridge, the composite, the flyweight, and the proxy. Each of these serves an equally critical, highly specific purpose in structural design, from saving memory with thousands of objects to controlling strict access rules. These are the tools that separate entry-level programmers from senior systems architects, and we're going to continue to uncover their secrets in future deep dives and coding activities.
So I want to leave you with a challenge. After everything we've covered today, take a hard look at your own code. Where are your systems too tightly coupled? Where does a simple change in one file cause a massive cascade of errors in another? Most importantly, which structural pattern could save that code? Are you forcing incompatible APIs together without an adapter? Are your classes way too complex without a facade? Stop just writing code and start architecting brilliant, flexible systems. Thanks for joining me in this explainer, and I'll catch you next time.